I'm Steve Collins. I'm an associate professor of mechanical engineering, and I direct the Stanford Biomechatronics Laboratory. We design wearable robots to help improve people's efficiency, speed, and balance, especially for people with disabilities like amputation or stroke. And this is a really tough design problem. The main challenge is that it's hard to predict what kind of device a person would benefit from because we're so complicated in our bodies and our brains. We're all unique and we're constantly adapting and changing. So we've been focusing on ways of improving the design process itself. One of the sets of tools we've developed are versatile hardware systems that we call universal device emulators. The person wears a lightweight prosthesis or exoskeleton that's tethered to powerful off-board motors and computers. They can get the physical experience of interacting with a wide variety of devices without the overhead of building these specialized products. So we can get a person's response to some new hypothetical device in days or even minutes rather than years, and that really speeds the design process. Of course, there are lots of different ways that we might try to help a person to get around, and so we need tools for searching this vast space of potential assistance strategies. So we've been developing algorithms that automatically discover and customize and continuously adapt assistance. We call this human-in-the-loop optimization. We measure a person's performance while they're using a device, feed that information back to an optimizer that then systematically varies device characteristics until the person's performance is maximized. And this works really well. For example, using emulators and human-in-the-loop optimization, we recently showed that an exoskeleton worn on one ankle can reduce the energy cost of walking by 24%, which is huge. And we're now extending the technique to devices that assist multiple joints, to new activities like running, and to improving other aspects of performance like speed or balance in the presence of big disturbances. We're also beginning to work with people who've had a stroke. Post-stroke gait is more effortful, slower, and balance is difficult. And we think that optimized exoskeleton assistance could help with all of these things. We're also starting to work with people who've had lower limb amputation. Conventional prosthetic limbs replace many of the lost functions of the limb, but people with amputation still experience reduced mobility. A particular challenge is balance. Even just walking across a soccer field can be really difficult. The problem is that existing devices are unable to respond to little changes in the environment. So we're working on new prosthesis control techniques to try to enhance balance. Now that we're finding ways of really improving mobility, we're working on translating these into efficient and low-cost mobile devices that could become products. For example, we've developed an exoskeleton with passive clutches and springs that uses no energy itself, but reduces the energy cost of the person wearing it. And we've developed new ultra-low power, electrically controllable clutches that open up exciting new ways of actuating prosthetic limbs and exoskeletons. We're working with the companies that have spun out of our lab to try to get these devices out into the world where they can really help people.